So let's solve for our second problem, but this time we would be solving for a composite section. So your composite section is basically a combination of two or more basic shapes. So the most common basic shape, the most common composite section is that of your I sections, or let's say your wide flange or your I beams. So as you can see here, this is a composite section. So it is the combination of plenty of shapes here. So we can divide this I shape right here in this manner. So this is to be one section. This is to be one section right here, or one shape right here. This is to be another shape. And this is to be another shape. So this is a composite section because it is the combination of three rectangles. So that is for composite shapes. So in this composite section, determine the moment of inertia of the shaded area about its centroidal axis x and y respectively. So in this figure, we have this rectangular section right here, but there is a circular hole in the middle. So how can we solve for that? So if we are to solve for the moment of inertia about its centroidal axis in x, so let's say that Ix is equal to, so what we would be doing here is that we would be getting the moment of inertia of this whole section right here. And after that, let us subtract the moment of inertia of this circle right here. So it would be as simple as that. So for your I's of x, so what would be the moment of inertia about this section right here? So I would just be coloring it yellow. So what would be the moment of inertia of that section? So going back to this formulas here, so your I's of x is equal to bh cubed over 12. So that is to be b, our b is to be 150, our height would be 200 mm. So substituting known values, that is to be 150 mm times 200 mm cube divided by 12. So that is the moment of inertia of this whole section right here. But once again, there is actually a hole here. So what we would be doing next is that we would be subtracting the moment of inertia of this circle right here. And it has a radius of 50 mm. So going back to this database right here once again, so the moment of inertia of a circle is either pi r raised to 4 over 4 or pi d raised to 4 over 64. And since what is given in the problem is the radius, we would be using this formula right here. So from that, minus pi times the radius, and the radius here is to be 50 mm raised to 4. So we would be dividing this by 4. So do we need a transfer formula here? So basically we don't, because the centroids of the rectangle, which is this yellow fraction right here, and the centroid of the circle, which is this, coincide with your centroidal axis. So if you are to add plus AD squared, the value for your D is equal to 0. So this would just simply cancel out. So there, substituting known values, Ix is equal to, so looking once again to the calculator to your left, our answer for Ix is now equal to 9,509,1261.48 millimeter raised to 4th. So that is for the value for Ix. So we have already solved for Ix. Now let's solve for Iy. So for Iy, let's just denote it with this blue color right here. So Iy is equal to, so same approach as with this one. And once again, we wouldn't be needing the transfer formula since the moment of inertia about the y-axis is to be here, and its axis coincide with the centroidal axis of the whole section. So Iy, that is to be equal to, so once again, bh cubed over 12. So this is for rectangles. But the thing is, we would be considering this axis right here. So we would be considering this axis right here. So your new base is equal to 200 and your new height is equal to 150. So instead of 150 times 200 cube, it would be 200 times 150 cubed. So this is for IY. So divided by 12. So minus pi times 50 mm raised to 4 divided by 4. So once again, we would be subtracting the moment of inertia of this area right here, since this is to be hollow or it has a hole. So substituting known values, that is to be, so our answer here would be 513,41261.48 millimeters raised to 4. So this would be both of our answers right here. So IX and IY. So it would be as simple as that. But let's have another example, but this time we would be using our transfer formula. So in this problem, determine the moment of inertia of the T section shown in the figure about the centroidal axis x sub 0. So this would be your centroidal axis right here. So how can we solve for this? If you can see here, we don't have a formula for T sections. So what we would be doing is that we would be dividing your area into distinguishable areas. So I could just divide it here. So if I want to divide our section here, so as you can see here, we have a rectangle here and another rectangle here. So let's denote it as area 1 and area 2. Area 1, and the one on the bottom is to be area 2. So let's denote this as area 2. So for Ix sub O, that is to be the moment of inertia of the first area plus the moment of inertia of the second area plus the respective transfer formulas. I'll just be typing the general equation here, that is to be Ix we need to solve for the area, we need to solve for the distance from the axis, from their respective centroidal axis to the new centroidal axis, and their moments of inertia. But do we have the value for our XO? I mean for the location of our XO? So basically it is not given here. So using the knowledge that you have acquired in the previous pre-recorded lecture about the centroids, let's solve for the location of this XO right here. So I would just be typing here. So for centroids, so let's say that this is to be bar Y, and the value for your bar Y is to be the location of your x sub 0 from the bottom of the section. So computing for centroid, once again, if you can remember, the total area times bar Y is equal to area 1 times y1 plus area 2 times y2. And your y1 is to be this one right here. So if this is to be the centroid of your area 1, this distance right here is to be your y1. And for your area 2 or your y2, if this is to be the centroid of your area 2, this is to be the value for your y2. Okay, so for our area 1, let's solve for their areas respectively first. So for area 1, that is to be 2 times 6, which is 6 times 2. So solving for that, that is 12 inches squared. And for our area 2, this is to be 6 times 2 as well. So 2 times 6, that is also 12 square inches. And for our area total, that is to be the sum of area 1 and area 2. So getting their sum, that is to be 24. So 24 square inches. So that is to be for 80. What about for y1 and y2? So for our y's of 1, that is to be 6 plus half of 2. So it would be this dimension right here plus the half of 2. So 6 plus 1, that is to be equal to 7. And as for your y sub 2, that is just half of 6 since this is a rectangle. So half of 6 is equal to 3. So substituting known values, so our 80 is equal to 24 square inches times bars of y is equal to our area 1, which is 12 square inches, times y sub 1, and our y sub 1 is equal to 7, and plus a sub 2, that is to be 12, times your lever arm of the centroid, which is 3. So solving for the value of y, that is to be 12 times 7 plus 12 times 3 divided by 24. Our answer for bar y is to be equal to 5 inches. So meaning, from the bottom of your section up until your centroidal axis, that is to be 5 inches. So I would be deleting this for us to have space. For the moment of inertia of A1, about this point right here, that is to be the moment of inertia of area 1 plus AD squared. And the moment of inertia of the second area about the centroidal axis is to be I x sub 2 plus AD squared. And if we are to get the total of this, if we would be adding I x sub O sub 1 plus I of x sub O sub 2, that is to be equal to the total moment of inertia about the centroidal axis I x O. So there we would just be solving for these quantities right here and just get its summation for us to get the total moment of inertia about the centroidal axis. So let's solve for I sub x sub 1 first. So for area 1, so this is to be 1 over 12 times bh cube, and our b is equal to 6 and our h is equal to 2 cube. So that is to be 6 times 2 cube divided by 12. So our answer here is to be 4 4 inches raised to 4. And for your i's of x sub 2, this is to be 1 over 12 times bh cube, and our b right now would be 2, and our h is now equal to 6 cube. So our answer here would be, so 2 times 6 cube divided by 12. So our answer here would be 36. So there, and since this is to be our area 1 and area 2 respectively, let's solve for D1 and D2. So for D1 is to be the distance from your centroid of your area 1 up until the centroidal area axis. So it would be this one right here. So that is to be this of 1. So for your this of 1, since your barred y is equal to 5 and the total of this, so the total height of your composite section is equal to 8. So this is to be 8, but our barred y is equal to 5. So this one right here is equal to 5. So for your this of 1, that is to be 8 minus 5. So if you would be subtracting 8 minus 5, it would be this dimension right here. But we must subtract this dimension right here just to get the dimension of its centroid up until this point. So that is to be 2 inches. So y2 inches, this is to be 5 inches, this is to be 8 inches, and this one is to be 1 inch. So that is by inspection. And as for D2, so the value for your D2 is this one right here. So this is to be for the value for your D sub 2. And for your D sub 2, since the distance of your barred y is to be 5, so 5 minus the half of 6. So this distance right here is equal to, so 5 minus 3. or 5 minus 6 over 2. And our answer here is equal to 2 inches as well. So 2 inches. So now that we have our moments of inertia of those basic shapes plus their respective areas and their respective lever arms, or the distance from their centroids to the centroid of the axis that we have, that we will be considering, we can now solve for the total moment of inertia about that point. So I of x sub O is equal to your moment of inertia of the first area, and that is to be equal to 4 inches raised to 4 plus AD squared, which is the transfer formula. And for the first area, that is to be 12 inches squared times our distance 2. So it would be this one's right here. So 2 inches raised to 2. Okay, so that is for the first area. So for the second area, we would be adding here the moment of inertia of the second area, which is 36 inches raised to 4 plus, so what would be the transfer formula? It would be this one right here. So that is to be 12 inches squared times 2. But wait, I would just be moving this for us to have space. So times 2 inch squared. So solving for this, our I sub x sub O is now equal to, so 4 plus 12 times 2 times 2, so this is to be the ones in red, plus 36 plus 12 times 2 times 2, so this would be the ones in green. So solving for that, our value now is equal to 136 inches raised to 4. So this would be your centroidal moment of inertia about the x-axis.